Now that we've talked a little bit about how radiation affects us, we're thinking about where does it come from.
Okay, so we can understand the different types of radiation, how they affect things. Alpha really damaging locally, but blocked easily. Gamma really kind of dispersed damage, much, much harder to block. And so when we start to think about measuring radiation, we have two kind of different reference points. Are we measuring how much radiation comes out of the nucleus? Or are we measuring how much radiation gets into a person and causes effects on that person? And so the first question would be, how radioactive is the source? So a becquerel is a common unit there, which is 1 decay per second. Okay? And so that would be 1 decay event. That means 1 nucleus undergoing a decay process per second. So it's a rate. And so something that has a higher becquerels is more radioactive. There are 2 ways that a source can be more radioactive. 1, more nuclei. If you have more nuclei, there's more potential decay events. And 2, if you have shorter half-lives, which means it's more often that a nucleus decays. Both those things increase, you can really double down on how radioactive your source is. So for example, if you have uranium, 1 pound of uranium is about a 1.4 inch cube, so 1.4 inches on each side. Uranium is just a gray metal. So uranium-238, that has a half-life of 4.5 billion years. So that means 1 milligram of uranium is 12.4 becquerels. So 1 milligram of uranium corresponds to 12.4 decays per second. So in the case of uranium, that's alpha emission, so 12.4 alpha particles per second. If you have a pound of uranium, you would be getting 5.62 times 10 to the 6. So 5.6 million alpha particles per second. If you think about it, this is a pound of uranium. This is multiple moles of uranium. That of 1 million becquerels, 1 million alpha particles, that's not a lot of atoms decaying. It's a lot of alpha particles potentially. Millions of alpha particles per second, but you have quadrillions of atoms in this block, of nuclei in this block. So that's a relatively low activity, but it is a lot of uranium. Okay, so from the person side, we would have energy absorbed, right? The biological effects of how much it gets into a person. So one of the kind of general measurement would be a gray. And so a gray is energy per mass. How much energy has been absorbed into a given mass? 1 joule per kilogram is a gray. That's your metric unit. Then you also have a rad, which is another common unit used. So a rad is, or 100 rad is 1 gray. So that would just be total energy per mass absorbed. The thing is, it's agnostic to the type of radiation and potentially where the radiation is. So you can also have units that are specific to absorption of radiation into people, depending on the type of radiation. So for example, a localized alpha particle absorption is more damaging than beta emission, more damaging than gamma emission. So you have kind of different conversions of energy from gray into sievert, which is again 1 joule per kilogram, but there's a little cook in the books. And 1 sievert is 100 rem, and a rem is Röntgen equivalent man. It's a bit gendered, but Röntgen was one of the scientists who worked in the early world of radiation. And so the idea of using sievert or rem is that it directly shows effects in people. So often when we talk about radiation, we're going to talk about rem as the main unit because it reflects the fact that, are you getting really high levels of, say, alpha particle radiation, or are you getting high gamma radiation? Or was the alpha radiation blocked? Was it into your shirt or was it into your eyeball? Where did that radiation go? Was it gamma radiation across your entire body, or was it just, say, in your finger? Something like that. And so, these ideas of, kind of overall that we need to monitor these ideas. If you've worked in any sort of radiation-based environment, this is giving x-rays, or if you've ever gotten an x-ray, you'll see that this woman who's administering is wearing what's called a dosimeter, which is measuring the dose of radiation that this person has received. Again, this is going to be measured in rem because that's what really matters as far as like a human dosage goes. How much, what types of particles have been absorbed and how many of them, with what frequency, over what time. You'll also notice she's wearing this red apron. That is lead. So she is blocking herself protecting herself from ionizing radiation. Again, she's using X-rays in this context, so she doesn't have she's not wearing 4 inches of lead because they're not gamma rays. X-rays are easier to block. All right, so let's look at what sort of doses and radiation. So one of the ideas is we want to get some kind of ideas as to what doses there are. So this is showing doses in millirem. So we'll start with the bad side. Over here, these are hundreds of thousands of millirem or hundreds of rem. And you'll note when we start to get into that range, we get things like death within a month. If you get huge amounts of radiation, you would have extremely high chance of death. You can get things like hair loss. Hair loss is the reason why you would lose hair, again, is all about cell death, localized. Your cells die, so you just lose all your hair pretty quickly. You can also just get sick, radiation sickness, you just get sick from it. You can also increase the risk of long-term effects, say long-term cancers at, say, tens of thousands of millirems, things that would be, pretty dangerous still. So those would be bad. So that is tens, if not hundreds of thousands of millirem, where we start to get real, either acute or chronic health effects that come from it. So the average person gets 300 millirem a year. So that's just natural background, the sun, the ground, the food you eat. There is some amount of natural radiation that comes from that. If you get an X-ray, say 1 millirem, if you take a flight, over the Atlantic, let's say 2 millirems. That's the reason why a flight gives you more is if you remember when we talked about carbon-14, that there's a bunch of radiation in the atmosphere. The closer you get to the sun, the more higher up you can atmosphere, the less shielded you are by the atmosphere. So you absorb more, the more time you spend in a plane. So like pilots get high doses of radiation, relatively high doses. Again, these are single millirems. You need thousands or tens of thousands to cause problems. Your body itself is radioactive, right? That would be because you have carbon-14 in you. You have other radioactive nuclei that you eat. They are radioactive. They are unstable. They're going to fall apart, say, over tens or thousands of years. So, every now and then, one that's inside of you will decay and emit radiation into you. Medicinally is also how it would work. You also would get some from just medical exams. If you lived at a high elevation in Denver, again, higher elevation is worse than, say, Maryland is almost entirely at sea level. So, you'd get a lower dose there. We're pretty good here. We're really low. But again, these are tens of millirems, not that bad. The ground is giving you more radiation than that. And if you go to space, if you were an Apollo astronaut, you'd also get more because then you just totally remove the atmosphere as a whole. So in terms of all the places where we experience radiation, they can be generally distinguished between artificial sources. So that is primarily medicinal uses, X-rays being the biggest one, but we'll talk about some others. Also just kind of chemical or nuclear industry, nuclear weapons. The nuclear weapons we just tested them in the air, so those isotopes are all still floating around in the atmosphere. Then about 3/4 of it comes from natural exposure, and we'll talk about some of these, but a lot of it comes from space. Just the space has, the sun is emitting radiation at us constantly. Not all of it gets blocked by the atmosphere. Most of it does, though, thankfully. And then also the ground is also radioactive. There's a bunch of nuclei in the ground. Some of them are going to be radioactive. Then the other two big ones are food and radon. So radon is actually the most common source of nuclear radiation exposure that you feel at any given time. And so radon is an element, right? And radon is a part of the decay series of uranium. So uranium undergoes a number of decay processes, and eventually it hits radon. And the reason why radon is important is because it is a noble gas. It's important to think when these nuclear processes are happening, you are changing the atom type. You therefore change its chemical properties. Uranium and radium want to be in chemical bonds. Radon is a noble gas. It does not want to form chemical bonds. So once the nucleus becomes radon, the electrons adjust, don't need to form chemical bonds, they become unstable. Those radon atoms escape from rocks. It's a noble gas, it's a gas. So it floats up. So what happens is that radon leaves the deep ground where it forms and eventually comes into the atmosphere. As far as gases go, it's one of the heaviest, so it tends to sink. especially in low areas of human structures like basements. So these radon nuclei are unstable. Radon is big, it's unstable, and so it's going to be radioactive, and it's kind of just hanging out in the air. So what are the decay products of radon? This is the most common form of radiation exposure. Well, if we want to know the decay products, we want to start by thinking about why is it radioactive? Why is it unstable? Radon-222 is one of the most common isotope, and it's the one that forms in the uranium process, or from uranium. And so why is it unstable? Well, it has 86 protons. That is too big. It's going to decay by alpha emission. Okay, so it's going to do alpha emission. Well, what does it form? Well, we know it's going to emit a helium nucleus. So helium-4, balance out the mass. 22, you lose 4, 218 is left. Balance out the charge, you had 86 protons, you lost 2, 84 are left. So that's polonium. So you make polonium-218, which is radioactive in and of itself and potentially a problem, but it's not going to be that much of an issue because it's not a noble gas. It wants to react, so it'll form a compound, it'll leave your air, and you release alpha particles, which, you know, if we think about, we get most of our radiation from radon because it's in our basements, potentially floating around. But hey, it makes helium, or it makes an alpha particle, no big deal, because alpha particles get blocked by your clothes. So, you know, clothes, it's going to damage your skin. Not the biggest of deals. But radon's a gas. What that means is you can breathe radon in. So you can breathe radon in, it can get into your lungs. And now that if it sits into your, once it gets into your lungs, it's going to sit there because it's very dense. It can emit alpha particles from inside your lungs. Now your lungs block them. It doesn't affect the rest of your body, but that's going to do a high damage to your lung cells. So this is a potential risk factor for lung cancer. So radon is the most common source of nuclear radiation that you interact with. Again, it's not a ton. It's not something you need to be afraid of, but you do need to be aware of it. If you've ever lived in an old house with a basement, you want to be aware of that. We don't have basements down here because it doesn't freeze, but if you go further north and if you live somewhere with old rocks, so generally mountains, especially like the Appalachian Mountains, there's a lot of old rocks there. You have a lot of basements. You kind of put 2 and 2 together, you can get higher risk factors for radon, which is potentially a cause of lung cancer. So what about food? So again, like we talked about with carbon-14, there are just nuclear or unstable isotopes floating around in the atmosphere. You breathe them in, you eat them. And so then they're just part of you. And so they're part of the food you eat. Food can potentially be radioactive. They're in, your body, they're in the water, they're all around. And so the thing is, one of the most common radioactive foods is a banana. Potassium-40 is kind of a perfect half-life. Potassium-40 is not, it's not stable, but it's about as long as you can get without being stable, right? It exists for a long time, but it does still emit. And so potassium has bananas have a lot of potassium in them. So one banana is about 15 becquerels. So 15 beta emissions per second. You get like a truck of bananas, they're dealing with thousands, millions potentially of emissions or decay per second. So again, I'm not trying to necessarily scare you that bananas are dangerous. They're not, right? This is just to show you that there's radiation all around you. If there's a couple of decays here and there, that's not really a big deal because again, it's a banana. You eat it, it's got a lot of health benefits just because it has potassium in it. So just because, especially whenever there's like any sort of nuclear issues, I was kind of this, oh God, there's potassium all around you already. You are emitting, you're full of potassium-40. It's in all your nerve cells. There's emission from that as well. What are the decay products of potassium-40? So to start us off, we want to think about why is it unstable? Right? We know that it's not too big, right? It's less than 83. So we want to look up the atomic weight. The atomic weight of potassium is 39.09. So 40 is not a lot bigger, but it's bigger. Okay, so potassium-40 is unstable. So this thing is going to decay. This is one of the reasons why it's not very unstable. You're not really too many neutrons, but there is a little too many. This is an odd thing as to why it's unstable. There's odd protons and odd neutrons. That's why it decays. So this does undergo beta decay. So we know we're going to emit an electron. Balancing the masses, 40, you don't lose any mass, so it's still 40. 19, you lost a negative charge, means it goes up to 20. So you get calcium-40. Really, the motivation here is calcium-40 is extremely stable. And so potassium-40 just can't really keep up. It falls apart to get to a really, really stable minimum with calcium-40. And so, again, here, it doesn't necessarily say that bananas are dangerous. You know, they're only emitting beta particles, relatively easily shielded, not the worst, even if you eat them. It's also inside of you as is. There's a lot of radiation around you as it stands, and bananas are a big part of it. They're not bad, though. They're not dangerous. Radon, you should probably get your house checked for radon.
Participation 424, question 1. Complete each of the following statements. Blank is the easiest type of radiation to shield. B, blank is the type of radiation that does the most local damage. C, blank is the largest source of radiation exposure to people. This is the first question of participation 424, due Friday, April 24th at 11:59 p.m. over on Blackboard. The link to the assignment is right below the document where these videos are posted. Again, complete each of the following statements. Blank is the easiest type of radiation to shield. Blank is the type of radiation that does the most local damage. And blank is the largest source of radiation exposure to people. Okay, got our first participation question for 424, due Friday the 24th. Got a couple more videos to go. See you there.